morning. We begin lecture 32 with a quick summary of lecture number 31. And then in today's lecture, hope to cover a lot of very interesting aspects of antenna diversity, from the simplest schemes to the more complex schemes, and then finally on to the optimal scheme. So again, all of this hopefully will build up intuition, will also build up a strong analytical framework and help us to work with the concepts of antenna diversity that are very important in the context of a wireless channel, particularly if you are experiencing a severe fading such as relay fading. A quick summary of what we have discussed in the last class. We have, through the various steps, have developed a model by which we can generate relay fading in a computer which satisfies all of the properties that we are interested in. This particular time domain model is referred to as the Jake's model. People don't even call it Jake's relay fading model, they just say Jake's model. Everybody assumes that you know what they're talking about. It's the relay fading simulation or relay fading waveform that is generated using the Jake's method. So Jake's model is very widely used, and this is something that I would like you to be very, very familiar with, comfortable with, and actually be able to program and use, because the model itself is quite simple. It is very versatile in terms of its application. So a typical Jake's model, a block that implements Jake's model, will ask for three inputs. One would be the Doppler frequency. The rate of fading depends on the Doppler. How much correlation is there between successive samples? That depends on the Doppler. It also depends on how finely you are spacing it in time. So the sampling frequency is also very important. And the length of the waveform that you are asking the fading block to generate is also an important parameter. So what comes out of it is a discrete time sequence, complex sequence, satisfies the properties that the real and imaginary parts are Gaussian, both have equal variance, equal to half, and then the autocorrelation satisfies the Bessel function as we have studied it in the analytical model. Okay. Most often the practical realization does not require you to have just one tap, but it will require you to have multiple taps. That means you have to call the relay fading simulator multiple times. If you just call them and not specify the random phases. So what is important is that you would have to set different random phases for each of them. So for example, this one you would have to set random phases theta 11 to theta n naught comma 1. Okay, so you would have to specify. This one you would have to specify theta 1 comma 2, theta n naught comma 2. Because if you did not specify these random phases, both of them will generate the same waveform, because there is nothing else that is different between the two. All of them have the same frequencies, all of them have got the same scale factors. So this is very important, that depending upon how many relay fading coefficients you want to simulate, you must generate that many random phases. Now typically you would want these to be uncorrelated with each other, basically that the fading is independent on each of the taps. Now this, as we talked about yesterday, does not guarantee you that the fading waveforms are uncorrelated. The only way to guarantee that there's uncorrelated is to use the dent variation of the Jake's model. So again, that is something that I hope you'll be able to read and understand and appreciate and also implement. The basic model of Jake's, just so that it's always fresh in your memory, there are n+1 oscillators with scale factors, which are then combined with a appropriate scale factor. The scale factor is to ensure that the variance is equal to 1/2. So you get the real part and the imaginary part, and you can then combine them to get a complex coefficient. In practice, these are not continuous variables. We use the discrete time, so t is equal to nts. You choose the sampling frequency and then you increment it by sampling frequency and then compute the model. So what you get out of this model is actually a discrete time sequence. So this would be ZR of n, this would be ZI of n with t equal to nts. Okay, that's the sampled version of the Jakes model, which is what we will need for our simulation purposes. Okay. Again, just to refresh your memory, there are n plus 1 oscillators. All of them have got equal weightage except the one at the Doppler maximum Doppler frequency. So if you think of it as a quadrant of a circle, then the one that corresponds to the x-axis corresponds to the maximum Doppler, and then all of the other oscillators are evenly spaced in that region. The modification, so in a sense, the Jakes model satisfies the properties of zero mean, the complex Gaussian random variable having unit variance, and the appropriate autocorrelation function. What we specify is the Doppler frequency, length of the waveform that we want to generate, and also the number of oscillators that we are going to use. So, and this is not length, this is sampling frequency. So, this is the sampling frequency. Okay. So, n naught is also needs to be specified, because n naught is a variable. Typically, we take n naught greater than or equal to 15. That is more than sufficient to get the correct statistical behavior, but you can choose a larger value, because a larger value gives you a better approximation of the trapezoidal approximation. Okay. So, phi 1 to phi n naught are chosen randomly, and this is the waveform that is obtained. A quick observation: very often we want to generate multiple uncorrelated Rayleigh fading, multiple uncorrelated Rayleigh fading coefficients. And we will see today in a few minutes why these multiple Rayleigh coefficients are being generated. Multiple uncorrelated Rayleigh fading waveform coefficients, both are. Okay. Waveform is what is actually happening. Coefficients are when you observe it at an instant of time, you get a sample of the fading waveform. So, if you, this is the goal, that you want to generate multiple uncorrelated ones. The Jakes model gives you a way to do that. You have to generate it using the randomization of the thetas. But a guaranteed or an improved method is given by Dent et al., where it says shift the oscillators slightly. It's anyway a trapezoidal approximation. So, between this and this, there is not a big difference. This model allows you to interpret all the oscillators have got the same weighting function, which then interprets it using the Walsh-Hadamard, the first row of the Walsh-Hadamard matrix, and then that tells you that the subsequent rows of the Walsh-Hadamard matrix can be used to generate any uncorrelated waveform, waveform that is uncorrelated with the first one. Okay. So, maybe to summarize, in the Jakes model, I'll just add a couple of comments to the right hand side. We have used the following results in our derivation. J0 of x, we have used the expression 2 by pi 0 to pi by 2 cosine of x cos beta d beta. Okay, that is the expression for the J naught, and we have used the trapezoidal approximation. Trapezoidal approximation of the integral. Okay, and that is what we have used to show that the waveform or the autocorrelation RZZ of t plus delta t for the waveform that we have generated is approximately some constant times J0 2 pi fd times delta t. Satisfies the correlation that we are looking for, the time correlation. Okay. So, that is a summary of the Jakes model. We will definitely encourage you to try out. We will at least give you 2 computer exercises where this will be utilized, and of course, welcome to try more, because as you can see, there are several things that can be verified or validated using simple computer experiments. Again, we will not implement the Dent model as a computer exercise, but you can see that changing it, once you have the Jakes model implemented, modifying it to implement the Dent method, then using that to generate multiple uncorrelated waveforms is something that I would definitely encourage you to try. Okay. The last point that where we ended last lecture was a notion of diversity. So the first experiment that we had done as a computer experiment was to look at the effect of BER in Rayleigh fading. So you took the AWGN graph, generated a Rayleigh coefficient, which then basically perturbed the SNR, instantaneous SNR. You computed the corresponding BER for the instantaneous SNR value, and then you repeated this experiment multiple times and then took the average. So this average is what we, this average BER is what we saw was reflected by this graph. Okay, I hope you are comfortable. You see the relationships. Now, the whole notion of diversity at an intuitive level says that it is along the following lines of thought, just to sort of explore the concept of diversity. In this above experimental scenario, if you now had the option of trying two random variables, basically let's assume that you had, for every instant of time, you had two Rayleigh coefficients. They will give you instantaneous SNRs, alpha 1 squared EB by N naught, alpha 2 squared EB by N naught. Previously you had only alpha, previously you had only the one term. Now you've got two, and you are allowed to choose the maximum of the two. There's no reason why you would choose the minimum, because that's the idea is that you want to get a better SNR. So you would choose the maximum of the two and continue the rest of the experiment as pretend as if nothing else happened. So all you are doing is the same experiment, except that the instantaneous SNR is not chosen from just one random variable, but it's chosen as the maximum of two identical Rayleigh random variables. And what you will find is that you cannot do worse than the previous case. You can always do either as good or better, sometimes much better than the previous case, and that's why you will see the green line. Is it possible that I will reach the blue line in this method? Pardon? If you keep increasing the order of diversity, then maybe eventually you will get to something that is closer to the blue line. But again, what you will find in this case is that there is something called the law of diminishing returns. As you keep trying this experiment over large number of variables, you will find that the benefit increasing from 1 to 2 is very significant. 2 to 3 is less, 3 to 4 is even less. So basically it's a law of diminishing returns, but our goal, as we have always said, is that it will be nice if we can approach the blue graph, AWGN graph. So this experiment, I would describe it as BER in performance in Rayleigh fading. We have not actually generated the Rayleigh fading, but we've got an intuitive experiment with antenna selection. And the antenna selection part actually happens here, where you are choosing between the two antennas, and that is that's an interesting observation that we will pick up. Okay, so let me start with an example that will tell us why antenna diversity or antenna selection diversity is a very good thing. Okay? So let's assume that you have a system which has the following characteristics. It has got two states. Basically, it is not all SNRs are not possible. It has got two states. One is called SNR1, the other one is SNR2. Okay? This is like a finite state system. So you can remain in state 1, or you can transition to state 2, and then you can transition back, or you can remain in SNR state 2. Okay? That's a very simple system. It's a two-state system. So you can take into account the transition probabilities. You can say what's the probability that you're in SNR1, what's the probability that you're in SNR2, and let's assume that all of that has been done, and the final result has been given to us. So this is a two-state model, a good state and a bad state. Okay, and there are several interesting scenarios of analysis based on this, but this is more for us to explain the concept of diversity. So based on the analysis of this finite state machine, we are told that probability that you are in state 1, SNR1, is 0.9. And probability that you are in SNR2 is 0.1. And the good news is that SNR1 is 13 dB. Okay, that in linear scale would correspond to 19.95. So if you are looking at a BPSK system, just so that you get a feel for the numbers, this would be Q of root 2 gamma, where gamma is 19.95. You can please do the calculation. This would be Q of 6.32. 6.32, this comes out to be 1.37 into 10 power minus 10. For a wireless channel, this is amazing. And you're very, very happy that one of your states, which is there 0.9% of the time, right? I mean, it's a highly probable state. And of course, interested to look at what is the other system. The SNR2, unfortunately, is not such a good one. It is 0 dB. 0 dB means the SNR is equal to, on the linear scale, it will be equal to 1. So the probability of error, not so good. This will be Q of root 2, which comes out to be 0.078. Doesn't look too bad. But anyway, compared to 10 power minus 10, this is not so good. So now we want to calculate the average BER. BER average, just like you did in the previous experiment. There were a huge number of SNRs possible because you were generating them instantaneously. It's a simpler version where we say that, okay, the average probability is 0.9 times BER1 plus 0.1 times BER2. BER2. Just do the calculation and you will find that it is 0.0078. What happened? No, where's what happened to your 10 power minus 10? Because that really did not contribute to the bit error rate at all. What was actually dominant, even though it was only 0.1% of the time, 10% of the time, is that it was is the bad SNR state. Okay. Now here comes the crucial observation. Supposing I told you that you had two antennas, both of which are in this environment, but they are independent of each other. Two antennas which are independent. Okay? For each of those antennas, the BER1 probability is 0.9, the SNR1 probability is 0.9, SNR2 is 0.1. Okay? Now tell me, what is the probability of SNR2 when I have two antennas and both of them have got identical statistics? What is the probability? 0.01, because both antennas have to be in the bad state, so only then you will be stuck with it. Even if one of the antennas is at the good state, then you will get the benefit of the. So this is 0.1 into 0.1, 0.01, which tells me that the corresponding probability of SNR1 under this assumption will be 0.99. Okay, now compute the BER. Improved, it goes up to 7.8 into 10 power minus 4. Okay. Just as an interesting exercise, try 3 antennas and you will find that it's even better. The average bit error rate goes up to 10 power minus 5. 7.8 into 10 power minus 5. So you're starting to see the benefits of the antenna selection diversity. So something that gave us not so good performance, with just by adding a second antenna or a third antenna, you start to see a huge benefit that is coming from the diversity process. So this is a very important element, and this is what we want to exploit, we want to understand, we want to make sure that we can get the maximum benefit. So the general framework says that if I have NR receive antennas, R stands for receive, because we will also talk about multiple transmit antennas where we will say the number of transmit antennas is NT. So NR receive antennas, okay, and if they are independent, that is each of them experiences independent fading. Now what do we mean by that? I have one transmitter, I have multiple receivers. So this is the transmit side, this is the receive side. The channel from only one signal is transmitted. only one signal is transmitted, but it's picked up by the two receive antennas. And what we are saying is this one experiences a Rayleigh coefficient Z1, this one experiences a Rayleigh coefficient Z2, Z1 and Z2 are uncorrelated, or basically they are independent, uncorrelated with each other. Okay? So each of these antennas are independent, means that the Rayleigh coefficients that they experience are independent of the others. So under this condition, what we will show is that in the best of scenarios, the average BER, I'll write a subscript NR, should be of the order of BER1 raised to the power of NR. Okay, raised to the power of NR. It is a exponential benefit that you will get if you do this is under the optimal combining. Okay, so that is why we are so interested, this is such an important concept for us in terms of the antenna and the whole concept of diversity. Okay, now we use the word combining, but what we have actually done is selection. Okay, so is selection a form of combining? Is it? The answer turns out to be yes, because the received signal with diversity we say is equal to A1 into R1 of t plus 1 minus A into R2, A1 times R2 of t, and A1 is element of 0 or 1. A1 is equal to 0 if gamma 2 is greater than gamma 1, A1 equal to 1 if gamma 1 is greater than gamma 2. In other words, you are going to just set binary weighting functions. So it is trivially a form of combining, but selection diversity also falls into the framework. It clearly may not be the optimal one. There may be better versions of it, and the goal would be is to find out what those best or most optimum versions are. Okay? But first, since we already know that selection diversity gives us a good benefit, we would like to first understand and establish a framework for the selection diversity. Any questions on what we have said so far as the concept of diversity, the benefits of diversity, the forms of diversity, and why we and the benefit and the impact that it will have in terms of our performance? Any questions? Okay, let me draw a figure for you which I hope will be very helpful in understanding the concept and also reinforcing whatever we have said so far. Okay, let's assume that this is the fade threshold, and I'm going to have two waveforms. So the first antenna has a signal that is following this pattern. The second antenna has the following pattern. Okay, so this is the fade threshold. This is the fade threshold. The blue lines are gamma 1. This is gamma 2. That means the SNR of antenna 1 and antenna 2. Now independently both of them experience fading, but you can see from the two graphs that their fade, the times when they go into a fade are not necessarily related to each other. When one is weak, the other one may be strong. So, but there are times when both of them are in trouble, because you can see a region here where they're both in trouble. Now the notion of selection diversity says pick the stronger of the two antennas. So the selection diversity basically follows the following dotted line. It says pick the blue up until this point. It's gone into a fade. Both of them are in a fade, but red is slightly better. You pick the red at those points. Then blue comes out of a fade. You take advantage of that. You follow blue. Then red becomes stronger. You take red. And then when red is going into a fade, fortunately blue is strong, so you completely avoid that fade. When blue seems to be dipping, once more red is picking up. So you can see that this would be the gamma selection diversity. If I did it correctly, at every point in time, I pick the stronger of the two antennas. Okay? So keep this picture in mind. Again, it hopefully solidifies whatever we have been saying so far. So let's quickly establish the analytical framework for selection diversity. So our basic premise is that the envelope of the fading waveform is a Rayleigh random variable. Again, this is just a recap, Rayleigh random variable. If I look at the random variable V squared, the random variable V squared, this is a central chi-square random variable with 2 degrees of freedom. With 2 degrees of freedom, again we have already gone, I mean we have seen this earlier, 2 degrees of freedom. And the reason we work with this one is because the instantaneous SNR can be written as the envelope squared times EB by N naught. And expected value of gamma is denoted by uppercase gamma. And all of this tied to a PDF which says that the probability density function of the SNR, probability distribution of SNR is given by 1 over uppercase gamma e power minus gamma by gamma. Again, this is a form that we have already developed. Okay, so that's our reference point. You can probably look it up in your notes or rewrite it just for reference. Now comes the framework that we are interested in developing. Probability that SNR1 is less than or equal to the gamma threshold. Okay, what is that? Basically, or maybe just write one more step. The CDF of f gamma of gamma is the probability, or gamma threshold is the probability that gamma is less than gamma threshold, which is given by 1 minus e power minus gamma threshold by gamma. Okay, we have already derived that result as well. Okay, this is nothing but the cumulative density function 0 to gamma threshold f of gamma f gamma of gamma d gamma. Okay, that's the expression that we have received. So what you're asking is basically the cumulative distribution function for gamma 1. Okay, this would be given by 1 minus e power minus gamma gamma threshold. Let's write, be consistent, th divided by gamma 1, where gamma 1 represents the average SNR of antenna 1. Okay. Now, if we were to extend it to M antennas, M independently fading antennas, so consider M antennas, you can call them as uncorrelated antennas, or so I'll write both. You can specify them as uncorrelated, or you can also specify saying that these are M antennas with independent fading. Okay, both are the same for us. Under this assumption and the fact that you are doing selection diversity, so selection diversity basically says gamma selection is maximum of gamma 1 through gamma M. You're going to choose over all of these M antennas, and the probability that your gamma selection is less than threshold. That means even under gamma selection, you are in a fade. So probability that gamma 1 to gamma M, all of them are less than or equal to gamma threshold. That's like saying the maximum is less than the threshold. That's just, equivalent to saying all of the antennas are less than the gamma threshold. Because they are independent, becomes product pi of k equal to 1 through M, 1 minus e power minus gamma threshold by gamma k, where gamma k is the average SNR of that particular antenna. Okay. Just one more step and we start to get some very, very interesting results. The interesting results start to emerge here with the first assumption, where we say that if all antennas are equally strong or they have similar statistics, if all antennas have similar statistics, another way of saying it is they are equally strong. Similar statistics, that's the same as saying gamma k is equal to gamma for all values of k. That means all of them are seeing the same average SNR. Then the probability of a fade, that is all of them being below the threshold, will be equal to 1 minus e power minus gamma threshold by gamma raised to the power m. Okay, very good sign, because you are starting to see the benefit of the diversity factor. It's in the exponent. Okay, it's not we have not shown it in the context of BER, but you've already started to show that the benefit is starting to come as a exponential form in terms of the order of diversity. Okay, now a couple of very interesting offshoots of this particular result. Let me share that with you, because that will be very helpful for us in terms of our understanding. So first one is what happens under strong signal conditions. Strong signal conditions. This is a very useful result. So under strong signal conditions says that the average SNR is much greater than the fading threshold, right? Average SNR is much stronger. Now under this assumption, what we would like to use is the following: 1 minus e power gamma threshold by gamma. Notice that the exponent is very small, so you can use the following approximation: e power minus x is approximately 1 minus x. That's a approximation when x is small. That's a fairly good approximation. So this can be approximated as 1 minus gamma threshold by gamma. Okay, so this is nothing but gamma threshold by gamma, and the probability of a fade, probability of a fade or probability of outage when there are m antennas, we said was 1 minus e power minus gamma t by gamma raised to the power m. Can see the direct exponent form. This can be approximated by gamma threshold by gamma raised to the power m, or in other words, this is gamma threshold raised to the power m by gamma raised to the power m. So the SNR comes very directly in terms of the benefit of diversity. Okay, so the key thing is these are going to have a huge impact, because if you had only one antenna, it will be gamma threshold by gamma. If you have two, it becomes by gamma squared, then gamma cubed. So you're starting to see the benefit of diversity under strong signal conditions. That is a useful result for us to keep. Okay, now comes a very useful practical result. Supposing one of the M antennas is weak. Okay, supposing one of them is weak. Now when can that happen? If you have a handset, one of them is an antenna at the top of the handset, one of them is in the body of the handset, and your hand is around it, then what will happen? The antenna at the top sees a better SNR than the one, because your hand is blocking part of the signal. So we cannot always assume that all of them have got similar statistics. One of them may be weaker. So if one of the antennas is weak, if one of the M antennas, so that means M minus 1 are strong, one antenna is weak. If one of the antennas is weak, what happens? Is weak. So without loss of generality, we will say that gamma 1 is antenna 1 is the one that's the weak antenna. So we will make the following extreme condition, that gamma 1 the average SNR of antenna 1 is actually less than gamma threshold, just to make the extreme case. All of the others are much above the threshold. Okay. So, now we are interested in the probability that gamma 1 through gamma m is less than or equal to gamma threshold. That is the probability of a fade. Like before, we will write down the cumulative distribution functions for all of them. 1 minus e power minus gamma t by gamma 1 into, the others are all strong antennas, so I can write them as gamma threshold by gamma raised to the power of m minus 1. Am I correct? The reason I could not make the approximation for the first term is because that approximation is valid only when the exponent is very small. Now, if gamma 1 is much less than the threshold, the exponent is actually much larger than 1. Okay. Now, very interestingly, if gamma 1 is much less than gamma threshold, this exponent becomes very, it becomes negative of a very large number. So, which means that this term is almost 0. So, what is the net result? A very, very interesting result. So, the net result is approximately gamma threshold by gamma raised to the power m minus 1. So, it looks like there are only m minus 1 antennas. Okay. It is a very satisfying result, effectively only m minus 1 antennas. From a selection diversity point of view, that is precisely the situation. One of them is very weak, you are never going to choose that one. So, you might as well, you can discard that one antenna and pretend that there were only m minus 1 antennas that were present, effectively m minus 1 antennas. Okay. So, the notions of diversity with intuition, with the analytical framework are very, very important for us. So, that is part of the reasons why we are trying to establish this aspect. Okay. Now, I would also like to ask you the following situation. Okay. So, the scenarios when antenna selection is not useful, scenario when antenna selection is not useful. Is not useful is if one of the antennas, basically if let's, when the case of two antennas, one of the two antennas is weak, right? If they have only two antennas and you have to choose between them, if one of them is weak, then it's not going to help us. So, here is the pictorial representation of that. So, this is the gamma threshold. SNR1, first antenna has got some SNR, so this is gamma 1. Gamma 2 is this. Notice it is always below the fading threshold, so it really does not contribute to the SNR benefit. Right. So, selection really, so in this is a case where it is no use. Do you see any other scenario when SNR selection will not be beneficial at all? Large scale fading, well, basically means that you are having some obstruction with respect to the transmission. That is this scenario. That is, one of the antennas is seeing more obstruction of signal compared to the other. So, this would be that scenario. So, so the large scale fading would probably be captured here. Any other scenario where selection has no benefit whatsoever? Both antennas are equally strong, but if they are independent fading, there is actually benefit, right? But they are not independently faded. So, basically the scenario where you will not see much benefit if the second antenna also had the same behavior. If this one also was having the same SNR variation, instantaneous SNR variation, then it does not add to the benefit. So, that is a second scenario. The antennas are correlated antennas. This happens to be a case where the correlation factor is actually equal to 1. So, whenever the original one antenna is in a fade, the other one is also in a fade. So, therefore, there is no benefit for this particular element. Okay. Okay, now a little bit of homework for you. If you go back and look at our notes from lecture 16, we plotted a CDF. Okay. The CDF basically what we plotted was to show the behavior of the envelope of a Rayleigh random variable. And if you plotted it for the SNR, you would find that the plot will look very, very similar. Basically, what we are saying is the probability that gamma is less than a gamma threshold, which we have just now shown to be equal to gamma threshold by gamma, and whenever this value is small, and or in other words, when gamma threshold is much less than gamma, and basically what we find is that the CDF is more or less linear. When you plot it on a log scale, you'll find that it is linear, and then eventually it will saturate. Okay, so please do look at that graph. For your just for as a reference, I've shown it, but it's more important that you actually go back and refresh yourself. That was done with the envelope. This is with the SNR. Envelope and SNR are just related by a square, so when you take the dB, there is no difference there. The plots on a dB scale is exactly the same. Okay, so this is a CDF, and basically the CDF, it's a normalized SNR. So what is normalized SNR? Probability of gamma divided by the average SNR less than what is on the x-axis, less than abscissa. Okay. So this is exactly what we have drawn before. What we had drawn before was this dark line. Okay. The line that is here is what we showed previously. You can verify that for Rayleigh fading that is the case, and confirm that even for the SNR you will get exactly the same cumulative distribution function. Okay. Now, when I have the option of selecting between two antennas, it becomes the first function, basically the high SNR approximation becomes this whole squared. So which means that now there is a different slope to the graph. So n equal to 2 you can see for two antenna selection, and then you can see for n equal to 3 the antenna selection. Basically look at all the solid lines. So you start to see that the CDF is changing. And what exactly is the CDF? What does it mean? So for example, let's take this point, 20 dB. What does that tell me? Probability that gamma by gamma is less than minus 20 dB, right? That's the probability. This is the same as saying probability of the instantaneous SNR expressed in dB is less than the average SNR in dB minus 20 dB. Okay? The probability that the instantaneous SNR falls 20 dB below the average SNR. That's exactly what the CDF is trying to tell us. Okay? When you had only one antenna, you had a fairly high probability that you could hit that bad point, that your instantaneous SNR is 20 dB below the average SNR. But notice when you have two antennas independently faded, that scenario is almost taken out of the probability is actually very, very low for that. Okay? And when you take three antennas, it becomes even less probable. So what this is saying is the probability of those bad SNR conditions, which is what is causes the fading, is actually very beneficially removed in the context of selection diversity. So actually by looking at this CDFs and by spending some time with it, you can actually get a lot of insight into the benefit. Don't worry about the dashed lines, that is for optimal diversity. So there is optimal diversity which will do better than the selection diversity, and this is just to show that, but eventually we will get to that point as well. So now comes the question of what are the types of selection diversity. Types of selection diversity, and it turns out there are two very important types of selection diversity. I will just quickly mention it to them, we won't spend too much time on those. The type 1 says that you have 2 antennas. I am going to draw the figures for 2 antennas. You can extend it for any number. I will select which of them is the stronger antenna and then pass it through a single receive chain and then pass it through the decision block. And then I get the output decisions. There is a type 2 where I take antenna 1, antenna 2, I pass this through Rx1, pass this through Rx2. That is, I'm not yet trying to decide which of them is the better signal. But having demodulated the signals, then I decide, okay, select which one you want to do. And the decisions from that particular branch are then are my final decisions. Okay. So basically, what is the selection happening? The selection will be maximum of gamma 1 comma gamma 2. If you had more than m and 2 antennas, basically it will be and that's the same for this one as well. You're trying to find out which one is the best option for us. Now the differences between these two is, in the one case you determine a priori which is the stronger of the two signals, and that you can do based on RSSI, received signal strength. Basically you take the signal strength from antenna 1, you measure it, receive signal strength from antenna 2. Now you know that not always RSSI is not always a good indicator of the SNR. Okay, sometimes it's not a good indicator, especially if there's a lot of noise present in the system, you cannot differentiate between the two. So what in this case you are doing is selecting on the basis of antenna, hoping that it's the same as maximum SNR. In this case, you can actually estimate what is SNR1 and SNR2, and then you can do the implementation more accurately, saying that, okay, I want to choose the best of these SNR. So the second one is called post-detection diversity. This is called post-detection. That means you detect which are both signals, and then you decide which one you want to choose. Post-detection, selection, diversity. And if this is post-detection, the other one has to be pre-detection. Okay, so that's the difference. Pre-detection simplifies the process because only one receiver is involved, but you have to decide ahead of time. You have to decide it based on RSSI, which may not be a very good indicator. On the other hand, this one, the second one, is a better option, but you notice that you have more complexity because you have to demodulate both those signals. So pre-detection, selection, diversity. Okay, just make a note of that. It's interesting for us to keep that just a mental note of how you would actually implement this in practice. All right, so now we quickly want to move into some of the other aspects of the diversity discussion, and I want you to leave with you some things for you to think about. We made the following statement, that a weak antenna did not really help us much. Okay, so that is a correct statement, but it has to be qualified. And here are some aspects that I want you to sort of think about, and then we pick it up from there in the next lecture. Okay, so the question is there any benefit from a weak antenna? Okay, we saw that selection diversity is sort of ruled out, but is there any benefit at all from a weak antenna? And it turns out that the answer is actually yes. And it's very important for us to know why the answer is yes and how come there is a benefit. Okay, so we will look at two particular scenarios. One of them is a noise limited scenario, and the other one is a interference limited scenario. So in a noise limited scenario, selection diversity basically says choose the maximum of gamma 1 comma gamma 2, and this is the gamma diversity. Okay, Now, the problem is this will always be equal to gamma 1 if gamma 2 is much less than gamma 1, because that is the weak antenna scenario. Okay. On the other hand, when we talk about optimal diversity, we will show that the signal that comes out from optimal diversity actually comes out to be gamma 1 plus gamma 2. Okay. That is one of the results of optimal diversity combining. Now, this has a huge implication, because let us consider the scenario that gamma 1 was less than gamma threshold, gamma 2 less than gamma threshold. What would have selection diversity have told you? You have no hope, right? Both antennas are out, you are in a fade. Okay. So, selection diversity says you are in a fade. You are in a fade, no chance, nothing to do. But optimal diversity combining, if I do gamma 1 plus gamma 2, I may be greater than gamma threshold, right. So, which means that first of all, even if I have gamma 2 is very weak, I will not throw it away, because under some scenario it may just add a little bit more to the SNR of gamma 1 and make me get some benefit out of that. So, that is one aspect that we need to keep in mind. The second aspect is when you are interference limited. Interference limited means that C over N plus I, carrier to noise plus interference, is approximately C over I. Okay, that is the approximation, and then we will look at this a little bit more. So, the model of the signal is R1 of t is equal to Z1 times S of t plus I1 times I of t. I is the interfering signal, I1 is the Rayleigh coefficient that is affecting the interfering signal, plus eta 1 of t. R2 of t is equal to Z2 of S of t plus I2 of I of t plus eta 2 of t. Okay. I am going to write down a statement which I want you to think about it. So, the signal strength Z1 squared is proportional to the gain of antenna 1. Z2 squared is proportional to the gain of antenna 2. The assumption that we have made is gain 2 is much less than gain 1. So, the question is there any benefit? The scenario that we are looking at is the interfering signal also went through the same gain antenna. So, I1 squared mod I1 squared is also proportional to G1, I2 squared is also proportional to G2, which means the carrier to interference ratio of antenna 1 is almost the same as carrier to interference ratio of antenna 2. So, under interference limited scenarios, I would never throw away a weak antenna, because the antenna it's also seeing the same carrier to interference ratio. Now, how come for SNR conditions it's bad, for interference conditions is not so bad? In fact, it may be a reasonably good option. I want you to think about it. We will pick it up from there and build on it. So, basically this is all that we have discussed today is in Molish chapter 13. Okay, and corresponding chapters on antenna diversity in Goldsmith and in Rappaport. So, please feel free to look at it. Molish chapter 13 will give you a good framework for what we have discussed today. Thank you. We will see you in the next class.